right, so it's 12 o'clock. All right. So, all right, so has everybody taken quiz? Hopefully everybody is here. Okay. All right. So, I know I told you I was going to give you your quiz back today, and that is true. Okay? But we're gonna do a little exercise. Okay? So, many of you are pretty well off, okay, I should say, or doing pretty well. I think this is Kristen Parker. Yeah, this is Sheila. Alright, so many folks are on their way, right? If they're not there already. Davis, Deshaun Davis? Davis? That's your name? Destiny? Yeah, Destiny. Lauren? Lauren? Lauren's not here yet. Clark Fisher? Clark Fisher? Layla? Layla? No. Dark Hato? No. Missy is not here. Jaden? Jaden? Alright. Silas? Joseph? Sakir? Crawford? Shayla Crawford? Durham? Linnell? Celia? Linnell? Raymond McDonald, not here. Alan? Yeah, right. Kinsey. All right. So. Miller. Braylon. Hughes. Knowles. Shaylin Knowles. Gianna. And Leslie Warren. Yes, sir. I think that's it. So, Leslie and Eddie, that's you. Alright, and Kristen Moore. What's your name? Alright. Alright. So, I think that's everybody. That's it, right? What's your name? Huh? Tonight. Okay. Alright, so that's everybody? Alright, so, well, I guess those folks who didn't show up, you might miss out. So, what we're gonna do is, we're going to redo this on Monday. We're gonna take the same quiz on Monday. So everybody in here should get 100%, right? Everybody in here. Because when we get to test 1, we can't do this. But on the quizzes, I can do this. Let's do this. So now I'm gonna put the ball in your court, and I'm gonna say, all right, are you gonna go back and correct what you made mistakes on? Because I've already provided you with the resources. It's up to you. You got the weekend. If it's something going on this weekend, you ain't got time, that's fine. We're gonna do it again on Monday. And we're gonna be quick. Maybe we might not even go the whole hour. Matter of fact, I'm gonna sleep on that this weekend, right? Because on Monday we should be done with it in 30 minutes. Because we know what to expect. I told you it's the same quiz. It's going to be the same thing. You did it once already, so you should know what you did wrong. If you don't know, then you got the resources to find it out. It's up to you. So let's keep moving forward. So all these people here, I don't know if these are your friends, right? Well, yeah. I'll excuse her because she's talking. But, you know, you can tell them. Maybe they want to track me down or whatever they need to do, you know. But we're gonna do the same quiz on Monday. And you got it already. You got the study guide. I know we love study guides, all right? All right. But we ain't gonna have no study guide on test 1, though. Just letting you know. This is the first half of the study guide for test 1. The second half of the study guide for test 2 is going to be quiz 2. All right? So let's keep moving forward, and let's do the lecture slides for chapter 2. And we're going to be, somebody hit the lights for me at the back. But like I said, many of you are in good shape. So just stay in shape, okay? And you'll be all right. Or you can get in better shape. Nothing wrong with getting in better shape. Oh, that's what I'm looking for. So we're in chapter 2, Newton's laws. Newton's laws of motion, right? Remember I mentioned to you at the beginning that the first part of physics deals with mechanics, right? So how things move, right? How objects move around, okay? That's the first part of physics, right? Because remember we talked about space and time and energy and mass, right? So an object that moves around, an object, if it's an object, that means it has mass. And we can put it on the scale and we can weigh it. We can say, oh, it's something, right? Because it has something, it weighs something, right? When we want to know the exact amount of something, we weigh it, right? When you go to the fruit stand or wherever, and somebody's selling you something that they grew, right? Some vegetables or something, they will weigh it to tell you exactly how much it is, right? And that's the way they can tell you how much you owe them, okay? So that's a physical thing, right? Weight. Weight is a physical thing. It is dictated by nature, right? By the laws of gravity. And that's what Newton is responsible for, right? Newton was sitting under the tree and hit him in the head. The apple fell out the tree because gravity made it accelerate towards the earth. Okay? So that's what we're talking about. We're talking about Newton's laws of motion. We're talking about objects that move through space and time. Right? Time is always there. Father time. That's why we say Father time. Time, you can't get rid of time. It always is there, and it's always going forward. Right? And like I said, if you have an object, it weighs something, so it has mass. If it has mass, then it has energy. So, like I said, we're going to talk about Newton's laws of motion, Newton's first law of motion, second law. We're going to talk about the forces and interactions, right? Third law of motion, and then we'll make a summary, right? But many of you are already familiar with many of these laws, right? So if I take a sheet of paper, or not a sheet of paper, a tablecloth, right? We've seen this on TV or whatever, right? Where people take the tablecloth and jerk it from underneath the dishes on the table, and the dishes on the table remain, right? So how do we explain that? Well, it's through inertia, okay? This is the first law of Newton, right? Newton's first law of motion. It's called inertia, all right? What is inertia? Inertia says that any object that weighs something has mass. I can put it on the scale and I can weigh it. If it has mass, it has energy. So that means if it weighs something, it has energy, then it wants to, if it's in motion, it wants to remain in motion. If it's at rest, it wants to remain at rest. That is the law of inertia, and we're all familiar with that, right? Anything at rest will remain at rest. Anything in motion will remain in motion unless acted upon by an outside force, right? So, what does that mean? That means that if I am an astronaut in space, right, and I'm working outside of the space station, okay, and some type of space debris comes along and provides a force and gives me a force and accelerates me away from the space shuttle. What happens? I'm asking y'all. Huh?
You go in that direction.
You will go in that direction, right? How far will you go? Infinitely. Yes. Because of inertia, right? Because in space, there is no atmosphere, right? So, there is nothing to slow you down. We live on Earth. Earth has an atmosphere, right? That's why we have something called what? Air resistance. We have air resistance here on Earth, okay? But in space, there is no air resistance. So if an object begins to move in a direction, it will move in that direction forever unless acted upon by outside force. And the same is true for an object at rest. That is inertia, okay? That's what we need to remember from first law of physics, first law of Newton, okay? Inertia, that one word, I, inertia, okay? We skip those, we'll deal with those another time. Oh, you know what? I'm on the wrong class, y'all. It's the same thing, but this is physical science. Let me open up y'all stuff. Get the real stuff. This PC. There we go. There we go. Okay. Here we go. That's y'all stuff right here. Well, I'll open up a PDF. There we go. There we go, yeah. All right, so, but it's the same thing, y'all. It's the same thing, right? So they just use bigger words with y'all, okay? So kinematics in one dimension, but it's still, we're still talking about objects that move, right? That's what we're talking about. We're talking about objects and Newton's laws, all right? They don't call the chapter Newton's laws, but no, actually, we don't deal with Newton's laws until the next chapter, or the chapter after that, actually. So I gave y'all the wrong stuff. I'm sorry about that. This is chapter 2 right here. Motion in one dimension. Sorry. Let's start over, okay? So, here is the contents of chapter 2, right? Reference frames and displacement. We're gonna talk about velocity, and we've already talked about that with the speed of light, right? We did our conversions on the speed of light and all that kind of stuff. So you ought to be seeing how this stuff is, how one chapter connects with the following chapter. That's how all STEM classes go. That's what we call stacked courses. Meaning, what you do at the beginning is important to what you're going to be doing at the end. That's how this goes, okay? So you should see how this connects to what we did in the beginning, right? Where we made all kind of conversion changes of length, time, and distance. All of those things dictate motion of an object, right? But that's the contents of the chapter. And of course, we're going to be talking about free fall, right? Free fall is an important concept from this chapter, right? Free fall is just basically constant acceleration due to gravity, okay? Gravity causes things to go into free fall, okay? All right, and so, as I said, these are the contents, and so you can read that for yourself, but we're gonna go through them real quick. All right, so any measurement of position, distance, or speed must be made with respect to a reference frame, right? So, they use this quick example, right? So if I'm sitting on the ground and I see a train pass by and somebody is on the train walking, right? Not only do I see them moving at the speed of the train, right? But I will also see them moving at another speed as well, right? With respect to the people sitting down on the train. Because everybody on the train is moving at the speed of the train. But this person, he's moving inside of the reference frame of the train. So to me, sitting on the ground, I'm on the reference frame of the earth, right? So when we say every position, distance, or speed is made with a reference frame, we have to say with respect to what? And in most cases in this class, we're talking about with respect to the earth, okay? Now, when we get in higher level physics and things like that, you might want to look at how things are moving with respect to another object that's moving. You know, that's relativity, right? And we start talking about, you know, a little higher level physics, okay? So, in order to properly understand how things move, we must understand the distance between, or the difference between distance and displacement, right? What is the difference between distance and displacement? Who took physics in high school? Somebody said they took physics in high school, right? Yeah?
I did, but it was COVID year, so we didn't learn nothing.
Oh, okay. All right. So distance and displacement, right? Distance. So if we think about somebody on a track, right, running around the track, right? So when they leave the starting line, then they run around the track, and then they end up back where? At the starting line, right? Well, that's a displacement of 0, right? Because for all intents and purposes, mathematically, not physically, mathematically, they went what? Nowhere. Because you started from one spot, you went somewhere, and then you end up at the same spot. Mathematically, we don't care where you went. What we care about mathematically, right, is where you start, where you end up. But physically, you know, because you saw it. You saw the guy on the track do what? Run around the track. So he had to cover a what? Distance. So his distance is not 0, but his displacement is 0. So do we understand the difference between distance and displacement? Okay. Displacement is the difference between the starting point and the finishing point. Distance is the actual length covered. Length over time. Or, well, no. Distance is speed times time, right? But you know what I'm trying to say. It's actual length, okay? Displacement is where I started, where I end up. So, quick example, right? So if we say here, we go what? 40 meters to the east, right? And we say, okay, well, if we go another 30 meters, right, then obviously, if we go another 30 meters to the east, then we're going what? A total of 70 meters east, right? So it matters when I say what direction, right? We have to say he's going east. Because what if we say, all right, well, if this person went 30 meters or 70 meters east and 40 meters, and then 40 meters west, then you're going to say, well, they end up at what? 30. Okay? So in that case, then the distance that they cover is how much? No. I said they went 70, then they came back 30. 100 is the distance. But what was the displacement? 40. Right? 70 minus 30. Okay? Good. All right. So that's basically what we were saying. That's basically what we just did, right? So that's just showing you here that it matters, right? Where we start, where 1 and 2 are, right? We start here, this is 1 here, and we start and we end up here, right? We have a displacement of what? 20. What? In what direction? East. Okay. So then, what's the displacement here? Huh? 20 meters going west. right? So here, x2 is 30 minus 10. Here is what? 10 minus 30. So in one case I have what? Positive 20. This case I have what? Negative 20. Are those the same thing? No, not hardly. Very much not the same. Okay? So when we talk about distance, even though we have the same distances here, 20, we have different displacements. Their magnitudes are the same, but they have different what? What's the D word? Directions. Right? One went east, the other one went west. Okay? So, that's basically the formulas, right? That's the formulas. That's how you would calculate, that's the difference between, so speed, you use distance. All right? But when we start, especially in chapter 4, like I was telling you, when we get to the Newton's laws, we're going to start talking about velocity. We're going to stop talking about speed, because speed does not indicate a direction. And so if I'm giving somebody directions to go somewhere, to go to New Orleans, I say, oh, well, just get on the interstate and go 75 miles. Is that enough information? What else must I know? What direction? You must say, I must go north, south, east, or west, or some combination of those. Right? But as you will see in chapter 3, in physics, we denote direction using angles. Right? So, a little bit of that funky geometry again. All right? So, what is this showing us? Right? So this right here, this is a straight line, right? Straight line. And this axis is what? Velocity. Okay? This is time, right? So what does a straight line at 40 tell me about this object? What is it telling me? What's constant? The speed of the object is constant. That's what this tells me. Okay? That's what it should tell you. Or we should be headed in that direction to get that kind of understanding. Okay? So I just looked at the y-axis. I looked at the x-axis. I said, oh, well, this is velocity. So it's at 40, it's a straight line. So it never changes, right? Right, this way. Right, never changes this way, right? So he remains, or she remains, or it remains constant at 40 miles an hour. So what does this one say? The speed changes, right? So when I started off, what happened? My speed shot up to 50. Then I did what? Remained at 50 for maybe about an hour, right? So this is what about, let's say this is what? This is 0.1, this is about, let's say 0.05, right? To 1.5, so that'd be about 1, right? The difference in those two would be about 1. So I say about an hour. About an hour they remain at 50, then what? Then it slowed down. And it went to what? It's right here. It slowed down. Then what? We slowed down to what speed? 20. And then it did what? Huh? Stayed constant at 20 for quite a while, right? And then when it got to oh, this is 0.1, so not an hour, I'm sorry, right? This is a 0.1, so this is a half an hour right here, right? So at a half an hour, then that says what? At a half an hour, it was traveling at 20, then at a half an hour, it did what? Stopped completely. Abruptly. Okay? So that's how you read these kind of plots. All right? And this is what you're going to be doing. Okay? This is what you would do in a lab course. Okay? But you don't have to have some type of understanding as well for the lecture. But particularly with the lab when we deal with data and stuff like that, plots and all that kind of stuff. All right? So this is just a cartoon showing you this, right? Showing you that T1, I'm at 0. My speed is at 0 at T1, so I'm at rest right here. The object is at rest. I'm like getting ready. I'm sitting there waiting to start the race. Okay? And then I go. I accelerate. All right? And I can accelerate. They're telling me what the acceleration is right here. Right? A is equal to this. So when I get to 1 second, right, that means what? My speed is at 15 kilometers per hour, right? How do I know that?
By your velocity.
No, not by my velocity, but by my what? You're close. By your acceleration. That's how I know that how fast I will be traveling after 1 second. Right? Is everybody following me on that? Nobody's shaking their head. So, acceleration. Let's talk about what acceleration is. What is acceleration? Somebody, tell me what acceleration is. You know what it is. You might can't put it in words right now, but you know what it is to accelerate. Huh? I didn't hear you. Somebody. Okay, for your, well, that was close. For your speed to change. That's what acceleration is. So your speed can be getting greater. We call that what? Acceleration. If your speed is getting smaller, we call that deceleration. Okay, so that's what acceleration is. It's telling us how fast the speed is changing. Not telling us how fast it's going. All of us have problems understanding that concept. Right? It's not telling us how fast it's going. It's telling us how fast the speed is changing. And you're going to get that eventually. Okay? When we get to, so if I take that same sort of logic, after 1 second I'm at 15, so after 2 seconds I should be at what? 30. Because I'm accelerating at 15 kilometers per hour per second. So that number should be changing at that rate every second. 30, right? So when I get to 5, I'm at what? 75. 5 times 15 is 75. Okay? So these things have to make sense, folks. We're not just making up things and calculating things and making it hard for people like, somehow some people just get it right and some people don't. No. There's one way to do it. Okay? So, as I mentioned to you, right, we could start off at a higher speed, 15, and then end up at a lower speed. We call that what? Deceleration. The car is slowing down. But it's still an acceleration. It's just a negative acceleration. Okay? All right? And, of course, we got to be careful when we talk about negative acceleration and positive acceleration, all those different sort of things, because, it can be tricky, and I won't try to give you any curveballs that are kind of misleading. But sometimes you can have a negative acceleration, but be accelerating in a positive manner, but still have a negative acceleration because you could be going in a negative direction. All right, but I won't try to confuse you like that. All right, so don't worry about that. All right, so this is what you would get if this was a calculus-based class. I'm just introducing it to you. I don't know why they put it up here, but I guess I know some of y'all took calculus 1, right? So y'all should be familiar with what they call this?
Limits.
Limit, which is a, what they call it? Nobody? Start with a D? What's a limit? A derivative. Alright? So, but we don't use derivatives, or we're not going to use calculus 1. This is an algebra-based physics course, so we're not going to use derivatives. So, but we are going to use a lot of algebra, and what we're going to be dealing with a lot of times is averages, right? Average. And everybody in here knows what an average is, okay? It's not something different from what you do all the time, okay? But here we have what? Average velocity of an object. So that's just the distance or displacement, I should say. Now we're in chapter 2, we're talking about displacement, not distance. Displacement. Because this is the difference between two positions, right? And then this is the time that elapsed while I was covering the distance between those two. Okay? And whenever you see this bar, that just says it's an average velocity. Okay? And that's not very important either. I'll tell you when it is important, okay? But it's not. Question?
I was just going to ask, do we have to remove this equation?
Yes. And I'm gonna, like I said, so what I'm saying is don't worry about it right now. Okay. Don't worry. Don't focus so much on this, because this is, there's other things you should focus on more. That's gonna give you more understanding. Then this is gonna be like, oh, this is nothing. Okay? Like these. Right? So this is how you calculate an average, right? If I had two speeds, if I have an object and it was traveling at one speed, then it slowed down, right? Let's say a baseball, a softball, right? If I'm throwing a softball and the softball is traveling, I don't know what kind of pitch it is, change up or something like that. It starts at one speed, or is that curveball? That might be with real baseball, I don't know, right? But I know that one of them starts off fast, then as it moves towards the plate, it gets slower, and that's how it kind of fools the batter, and they like swing too early, right? So that object has an average speed because it started at one speed, then it ended at another speed. So I take the two speeds, add them together, divide by 2, and that's how you get an average. Whatever I need to get an average of, if I got 3 speeds, I take all 3 speeds, add them together, then divide by 3. That's the average. So that's the average. So that's a way you can calculate the average speed too. It's an easier way actually, right? One that you should remember easy. Okay? But when we come down here, and I won't require you to know all of this, right? This is like a derivation. But this is what's important, okay? This right here, this equation right here. This equation right here. That's called the constant acceleration equation. And this equation is what governs projectile motion, which we will get to in chapter 3. But this is what governs projectile motion. So if I'm shooting a missile, like when the Army wants to shoot a missile and hit some place, then they can calculate, right? We can calculate at what initial speed does that missile need to go, right? Because it has to have an initial velocity in order for it to have enough energy to make it whatever distance you want it to make, right? Here's the distance right here, x minus x naught. So if I subtract this from this side, that's the distance that it's gonna travel, whatever that missile, right, with that missile. Here's the initial speed, and here's the time that it's gonna take to hit its target. And A is the acceleration due to gravity, right? Which is something that affects everything in the universe, right? Like I said, free fall motion is dictated by gravity. Okay. So here are some more additional equations, right? So this one right here is called the golden rule. This one we will use quite often. This one right here. We use that one quite often. Yes, you got a question?
Can you break that equation down again?
Which one?
The one you just got. The acceleration, constant acceleration.
So x is a distance, right? This is the distance that the missile, we're talking about a missile, right? We were just talking about a missile, right? So this would be the distance that the missile would travel to hit its target. This is the initial distance, which is 0, before it even took off. We just call it 0, right? And before it took off, it has not traveled any distance. So this is 0. So here, V sub O would be the initial speed of the missile, right? Because obviously, how fast the missile starts is going to determine how fast it, or how far it travels. So this is the initial speed of the missile, V sub O. T is going to be what? The time that the missile would take to hit the target. And A, which is the only thing you got left unknown, is the acceleration due to gravity, which is a constant, which we know. So I can calculate time and distance, as long as I know what? The initial speed of the missile. I can calculate how, if I want to hit this target this far away, I know when my missile will hit. Right? That's how they do it. Okay? It's physics. So a lot of these are just rearranged. A lot of all these other equations, they just rearranging. You can see this is the same one that we just showed, constant acceleration equation. But all of these equations live in the same neighborhood. They're neighbors. They all love each other. So they all get along. So they all should back each other up. Meaning, if I use a different set of equations to calculate something, then Dr. Stewart does, then it might not necessarily be wrong, right? Might not be wrong, right? Might be, but it might not be, okay? Because there is more than one way to solve these problems, okay? But just to let you know, word of caution, I would advise you to do it my way in most cases, okay? Just make it easier for you, okay? I'm not telling you that my way is the only way. I'm just saying, just do it my way. The way I show you. Now, that's not my way, actually. It's the way I show it to you. Do it that way. Because that's the way I'm able to properly assess what we're trying to do, okay? You do it your way, might still be right, but it might mess me up, okay? So that's why sometimes from instructors, they want you to do things a certain way. It's not because they just being an asshole. They just maybe want you to do things a certain way so they can assess you a certain way. All right? So when we solve these problems, there's a certain procedure you're going to use, and we're going to run through this, okay? But when we solve these problems, there's a certain procedure, and I mentioned this to you already, right? So we're going to go back to, I don't know when we got word problems. In the 6th grade, when did we get word problems? Elementary school? Something like that. Yeah, that's what we're going back to. We're going back to that. And we're going to make sure we got that under control. Because we lose that as we go through school, right? And I went through, I'm the same thing. I went through the same school as y'all did. Okay? We lose that over time. And so we need to get back to that and make sure we knock the rust off. Because that's a lot of people's problems with with physics, is that we forget those basic problem-solving procedures. Like, identify the question. See, most people don't do that. Most people see these things, and first of all, they're gonna get a little anxiety, and they're gonna start getting emotional, and and that's a normal reaction, right? If you go outside of the country and you don't know the language of the people, right? That's why they tell you when you leave the country, you should always know something. You gotta know something, some kind of way to communicate, right? And I learned that lesson the hard way, right? Went out the country, not knowing nothing. And when I got to where I was going and I tried to do something, I got a bad result, okay? It's because I didn't learn the language. It's the same thing here. You have to learn the language. That's the first step. You gotta learn the language. You gotta know what we're talking about, what I'm saying to you. You gotta know it. Because if you wait on test day to figure that out, then you're gonna lose, you're not gonna have enough time to do the physics and the math. It's not enough time. So the thing is to understand, that's my goal, is to get you to understand the physics right, get that out the way. So when you get to class, you can just do the math. That's how I know you understand the physics, even though I don't care about math. I know it sounds crazy, but it is what it is. So these are the steps, right? Remember, read the whole problem, make sure you understand it. Remember that? Decide on objects under study, blah, blah, blah. Draw a diagram. We're going to do that. I'm going to show y'all how to do that, right? I'm not the best drawing person. I can't draw, all right? But I can draw diagrams because it's for your understanding. This goes back to what we talked about in the first chapter with what? Models. What is a model? What's the purpose of a model?
Give an example.
So you can have better understanding. That's the point of a model. So that's what we're doing when we draw a diagram. We're creating a model. You created a model, your model, that you understand. Not nobody else, you understand it. So it's yours. Not mine, it's yours. Okay? Write down the knowns. Y'all know that, right? Because this is what most people want to skip to, right? Immediately when they're doing a word problem. They want to skip. Oh, all right. Let's wrap up. Okay, and that's the physics, right? So that's the solving problems. Here's some free fall information, right? Y'all know what free fall is. We don't have to talk about that. All right, but let's talk about this real quick and we'll wrap it up right here, right? So this is the lesson that y'all need to take away, and then y'all can go, right? So if I have two objects and I drop them at the same time, right? One basketball and one a bowling ball. Which one gonna hit the ground first? No!
Both of them.
Both of them what? Gonna hit the ground first?
At the same time.
That don't make sense.
They're going at the same time.
Okay, both of them gonna hit the ground at the same time. Why? Free fall. Free fall, right? Free fall. So they both will experience the same acceleration due to gravity, regardless of their weight. So that's the common mistake that people make, right? Right? It's like if the fat person jump out out the airplane and the skinny person jump out the airplane, no, they're gonna hit the ground at the same time. When will they not hit the ground at the same time? Then I'm gonna let y'all go. Oh, good. Did you take physics in high school? All right, well, all right. I'm gonna let y'all go now. So this is gonna be posted. I'm gonna post this, and let's just for video purposes, I'm just gonna keep going through it, but y'all can go. All right?
My question was, is it going to be open though since we got it back? Or
No, it's gonna be the same way.
Same thing, same question?
Yes.
Is the
Talking
question
about Monday?
Is the question
Wait, you said Wednesday.
Monday.
Monday. Yes, it's the same test, same quiz, everything the same. We're just gonna do the same thing over, and I've already posted the solutions, right?
With the questions?
Yes.
Oh, okay. All right. But I thought we was getting them back grade out.
No, the whole point of me giving it back was so you do not get a bad grade.
So I didn't let you last week.
All right.
I told you before I became a student here, I had a trip on me. I ended up missing an assignment, and I just realized I missed an assignment. I couldn't access it because I posted this.
Okay.
No
Okay.
access to campus.
Okay.
So that first assignment, I cannot do because he said
It's
it's
closed.
table.
Yeah. So you have to send me an email.
Again, okay.
Okay, do it again. Yeah. Sometimes I get so many.
No,
emails in
I
a day.
understand that. That's why I told you.
Right. So
But no,
just
I'll
send me.
record it and let
Right.
you know.
Right. Well, this is the way I remember it. See, some people just send the email and they never come to me and say anything, and they expect me to say something, and I might just, I got so much going on, I might not ever say nothing to you.
Because you didn't follow up. That's why.
Yeah. Yes. All right. So send it to me again. What's your name?
Kristen Moore.
Kristen Moore.
All right.
Did
Thank
you
you.
hear about the quiz already?
The what?
The quizzes?
Oh, yes, I gave it back. But we're gonna do it again on Monday.
Okay.
Did you hear what I was saying in class?
I
What's your
came
name?
in,
Who are you?
Celia.
Celia.
I came
Yeah.
in 10 after.
Okay.
Oh, that's fine.
No, this is
Right here.
oh. This
Yep.
Yep. Okay. So we're gonna do it again on Monday. Same quiz.
Okay.
Take it back.
Oh.
Right? You need it. All right? Hopefully you're gonna take that time over the weekend, right? And try to figure out what you did wrong, right? Because we put the video,
I know, I watched the videos.
so the video don't help you?
They did help. I just have a very bad memory. Like, I remembered it, then I'd be like, oh, well, what's this part?
Well, if you got a bad memory, that's perfect for me. See, I know you thought that was gonna help you. That's actually gonna hurt you, because I don't like people who rely on memory.
Well, I knew about the sophomore. I think I got that right.
Yeah.
It was just the speed of light. Or the light.
Well, go back to the video, right?
Mhm.
Compare what you did to what we did in class, and make sure you get it.
Okay.
Yeah, that's the point of this. That's what I'm doing. All right, because when we get to the test, obviously we ain't gonna do this. We're gonna get one shot. It's gonna be what it is, right? So I'm giving people opportunity to get a good start, right? With this quiz and the next quiz 2, right? Because test 1 is gonna be chapter 1 and 2.
Okay.
All right.
Thank you.
Good.